Hello everybody. I thought I'd do a quick lecture of Units 12 and 13 because these two units were pretty heavy in mathematics and some fairly complex topics. So because of that, I want to just do an overview of those two units. Again, there's very complex processes in there. There's a tremendous amount of math which I'm not going to expect you to understand. It will not appear on the final exam, I promise you that. I do want you to take a look at it and at least become a little bit familiar with some of the terms and some of the structures behind some of these complex control systems. You're not going to get responsible for anything on your exams. Just be aware of it and don't get overwhelmed. If you have any questions about anything that you see in this unit, please post your questions in the questions discussion topic in Blackboard. And if needed, we can also do a live online meeting to discuss any questions you might have. We can do these meetings either individually or as a group. A lot of the topics in Units 12 and 13 and really in the rest of this course are going to be addressed in much more detail in future courses within this program, where there'll also be some hands-on so you can demonstrate how these topics relate to process and to the process industry. Because the processes are becoming more complex today, the introduction of computers and either programmable logic controllers, but preferably programmable automation controllers, are coming into play in the process industry. The calculations that are required to do some of the instrumentation are becoming just too complex for the instruments themselves to handle. So we're going to talk about some of the calculations that are included in process today. And one of these is the algebraic sum or difference. In this block diagram that you see, this is calculating the error in the system between the set point and a process variable. So you have all been exposed to summing junctions in an earlier part of this course. And a summing junction is nothing more than an algebraic sum or difference. Here we're going to be taking a set point and we're going to be comparing it to feedback from a process variable and creating an error signal. What you're going to find is that a lot of control is done based on how much error do we have in the system. An error is calculated using the equation down here, either set point minus process variable or process variable minus set point. For the most part, you use process variable minus the set point, this bottom one. Having a problem with my pen today. If you're in a cooling application, and set point minus the process variable if you're in a heating application. And we'll talk a little more about that in the future. There's also an algebraic product or quotient. Now that we have the error signal in our process and we're going to use that for doing some control, we need to know what we're going to do with it. Well, here I have an equation which is the control variable is equal to the error times k sub p. And this is pronounced k sub p, where k sub p is the proportional gain. So there's a term that we're introducing called gain, and we're going to take the error signal and we're going to multiply it by some gain to produce the control variable. If you really think about it, this error signal can be quite small, and it gets small to the point whereby it will no longer have an effect on any control in the process. So we give it a gain term and basically amplify the error in order to give better control to our control variable. There's also a square root function. So in differential pressure flow meters, like an orifice plate type meter, pressure is measured before the orifice plate and after the orifice plate. The pressure difference is used to measure the flow of the liquid in the pipe. And there's a graphic here demonstrating that, and also the P&ID that shows a flow transmitter with a square root function block on it. If the pressure difference is more, the flow is more, and vice versa. So if the pressure system difference is lower, the flow is lower. The problem with this message is that the pressure difference is not proportional to the flow. So if the velocity or the flow of the liquid increases, the pressure increases, but at a different rate. If you were going to plot this on a graph, this would generate a curve. We like to deal with straight lines in control. Straight lines, linear lines are easy to control, but this particular function is going to create a curve. The curve does not do a good job in the automatic control requirements. So we have to make this curve a straight line. And we do that by using something called a square root extractor. And the instrument itself, and I lost there it is, uses a flow transmitter, and you'll see a little square up next to it, and this is square root. I know it's hard to see that that's a square root, but that's the square root, telling me that this is a flow transmitter or a flow transducer, with a square root extractor. And that will linearize this process. The equation for doing this is shown with Q equals CA sub T, the square root of 2 delta P over this symbol is the Greek letter rho, times the quantity of 1 minus beta, that's also a Greek character beta, to the fourth. The Q term is volumetric flow, and that's the flow rate. The C term is the discharge coefficient, and that's found on the manufacturer's specification sheets. A sub T is the area of the aperture face of the plate facing the upstream side. Delta P, that's this term right here, delta P, and this is the Greek capital letter delta. Delta means the difference or the change, is the pressure differential between the high and the low pressure tap. Rho, that's again this symbol, is the fluid density. So you'll have to know your fluid density in order to do this calculation. And the beta is the aperture diameter to pipe internal diameter ratio, which would just be D over D. So it's the aperture ratio, this diameter to your pipe diameter ratio. This calculation actually gets done in your controller. You don't even have to think about it, it just gets done, but you do have to supply the information to it. Other calculations include finding the highest and lowest value. Sometimes it's necessary to capture the highest or the lowest value that a variable has reached. You may need to know how how much pressure did this system actually have on it? You know, what is the highest amount, or what is the highest or the lowest temperature that this process reached? Another one may be that you have to limit a signal to a high or low limit. So as an example, there might be a process where the pressure cannot exceed 80 psi, and therefore you set a limit so that the pressure cannot go above 80 psi. Yet another function then is called a function generator. Now, a function generator is, I never actually heard this term before this, I read this text. However, the automated system and process control use devices that create an output signal that is a function of the input signal. The devices are literally called sensors in conjunction with either a transmitter or a transducer. So the sensor, and it shows here in this block diagram, I have a sensor here, is converting a signal into a different form that is compatible with the controller input. So in this example, a temperature sensor that consists of a thermocouple will create or will convert a millivolt signal that's generated by the thermocouple into either a 4 to 20 milliamp signal or a 0 to 10 volt DC signal. This block diagram that's on here is depicting the sensor with a measured variable C, so I'm measuring my temperature and I'm depicting that with C, going to a signal conditioner. So here's my sensor, and I'm using the thermocouple, which would just be a thermocouple, which is generating a millivolt signal. Some of them generate a microvolt signal. Sensor output coming to a signal conditioner, and that signal conditioner is converting this millivolt, microvolt signal to a signal that's compatible with the input of the controller that you're going to. So it may be 4 to 20 milliamps, 4 milliamps to 20 milliamps. It might be 0 volts DC to 10 volts DC. It might be minus 10 to plus 10 volts DC. But it's going to be something that's compatible. So therefore, if you hear the term function generator, it's nothing more than a type of control whereby the output is a function of the input. Another calculation that's often used and used quite a bit is first order lag. And you read about first order lag, I believe it was back in Unit 8 of your textbook. The first order lag basically states that when the input of a process is subjected to a step change, the output begins to respond either at time 0 or at the time that the step occurred. So this graph on this slide is depicting a first order lag. The step change is being shown with this red square wave, and that's this red line right here. You can see that it went up, it hides behind a grid line here, but right here, so right at this point here is where the step started, the step change occurred, this is the upper part of it, and then this is where the new limit is, or the new set point is. The process now starts responding to that step change. So this process starts to come back up to the new value. And you read earlier in the text that this change, or the response of your signal, should take less than 5 time constants, or around 5 time constants. So what I did here was I marked the first time constant occurs at 63.2%. The second time constant occurs at 63.2% of what's left over from the first time constant. So what was left over here from this first time constant was 36.8%. So if you take 63.2% of that, you get 86.4%, and so on and so forth until you get to your fifth time constant, at which case your process should be at the new level of the step change. The first order lag is described by an equation that looks exactly like this, where C, and that's this C term, is the output. R, that's this guy right here, is the input. K is our gain. And this symbol right here is the letter tau. That's T-O-U. It's a Greek letter, tau. Represents the time constant. And dc dt is referred to as a heaviside operator. So here it is in block diagram form. I bet you some of you thought you're never going to have to use that block diagram forming again, where we have our R, which is the input. Here's our output, and the equation being executed within this block is the gain over 1 plus the time constant, and P is the heaviside operator, dt, ddt. And that's what this is pronounced as. This is pronounced d dt. So what exactly is a heaviside operator? Well, a heaviside operator is calculus. And I hope that doesn't look like you saying, calculus? Calculus? I have to do calculus? Well, don't worry. If you never had calculus, you will not have to do any. However, you should know that there is a lot of calculus in process control, and you should understand what some of those terms mean. So a first order lag, or a heaviside operator, is a calculus term called a derivative. So when you see this term of d dt, this is equivalent to a derivative. In process control, when a loop is being tuned using proportional, integral, and derivative terms, or PID, the derivative term is also referred to as rate. So the derivative is nothing more than the rate of change of a process signal with respect to time. So we get the rate of change, d dt, with respect to time. So let's take a look at this graphically. Here I've got my same step change that I had with the process variable responding to that change. The derivative term is measuring the rate of change. How quickly is this process responding to this step change? So if I took a point, like right here, and I drew a tangent line to it, I'm going to draw a not a very good tangent line, but hope you get the idea. Tangent line to that. I then can calculate the slope of that line. And if I plot the next point and I draw a tangent line to it, I can calculate the slope of that line. But with calculus, if I draw a line that connects these 2 points along with the tangent point, that line is called a secant line. As I measure points, as I take points along this curve, and that's all I'm doing. I'm measuring the change. I'm measuring the rate of change. Remember what the slope term represents, is rise over run. That's all I'm doing here, is doing rise over run by measuring the x and y terms and calculating slope. That eventually I will get a point, I will get a point up here where the tangent line is parallel and the previous point, the secant line, is on top of it. So when the slope is equal to 0 and overlays the secant line, I'm at my set point. And I have no more change in the process. So all the derivative term is doing rate of change. And it's depicted dt. So it's not a very difficult concept to understand. But again, you don't have to do the calculus involved with this. But that's what this is doing. That's what the derivative term does in the PID equation. You also have the integral function. An integral is also a calculus term. It's the I term in the PID control loop. The integral portion is used to change the output of a process by the amount that's proportional to an error over time. So we're not looking at the rate of change of the error, we're looking at how much error is in the system over a time period or over various time periods. Mathematically, it's represented as E plus 1 over t to the sub I, and this symbol is the integral symbol. And this means the integral from 0 to t, which is time, error dt. So this is the error. 1 over ti is the time, and this is the integral of the error over time. So we'd like to look at the graph. Here's our graph again, and all I did was I magnified it so we could see it a little better. And our derivative term is going to have the most effect where the process signal is changing. So my derivative term is doing a lot of work in this area because, you know what, it looks at this point in time and it says, you know what, I still have an error here, and here's my error. I still have an error. I got to provide more power to the system, or more current or more voltage. And as the process comes up, I have more error here. I still have error. So the derivative term is taking effect here. I have more error, but notice that my error is reducing. I'm getting less and less error in the system. Less and less error. So as I get less and less error, my derivative term is going to be doing less or having less effect on the control of the system. Right now, the integral term really is doing not much at all, but the derivative term is the one that's taking charge. Now I get up to these points, like right about from here and on. I still have error in the system. Notice I am still not at set point, so I still have an error in the system, and I still have an error in the system, and I still have an error in the system, and we're plotting this against time. This is time. So this is where the integral term takes charge. The integral term is looking at this error over a period of time, and it's saying, you know, at this time period I had an error. And at this time period, I still have an error. So I'm going to supply a little bit more energy to the circuit to try to bring this error back home, back up to the set point. And at this point in time, well, I still have some error in the system at this point in time. So the idea of the integral term is when I have this little bit of error in the system yet, and I still have some error there, the derivative term isn't going to be doing anything because the slope of that line is equal to 0. The proportional term isn't going to be doing anything because the proportional term is basically what we saw before, where it's the error times the gain. So the error is very small, which means that it's not going to be doing a whole lot. So I'm really needing the proportion or the integral term to try to get rid of this small little bit of error in the system. The other calculation that can be done in an advanced system is lead lag. Lead lag is an advanced topic in the control systems, and we're not going to talk about this a whole lot here. It'll be addressed in another course, and you're going to be able to demonstrate it with using some process setups to see lead lag. But the output of this type of control system is defined using a differential equation. This right here is the differential equation used to do lead lag, where again K is gain, and then tau 1 and tau 2, where tau 1 is the lead time constant, tau 2 is a lag time constant, and this P is that heavy operator, which is the derivative. A lead lag system is often used in a situation where you have air-fuel control systems, where increases in combustion air flow lead to increases in fuel flow, and decreases in combustion air flow lag decreases in flow control. And again, you're going to be covering lead lag in a upcoming course. This unit also talks about ratio control. And ratio control is a strategy used to control a secondary flow to the predetermined fraction or flow ratio of a primary flow. Your textbook has several examples of processes that use ratio, and they're fairly good. I like to use this particular example where this ratio control is creating soda pop. And we have a colorant coming in. So here's our colorant. And we have this coming through a pipe, and it's at a fixed flow rate. We have a sensor here which is measuring color. And we're sending this signal up here to this summing junction and to this summing junction. This summing junction has a set point of the color to soda water ratio. So this is a set point to tell me the ratio of the color to soda water. And this output is controlling a motor-driven valve, which is also adjusting the amount of soda water coming into the system. And there's a flow meter to tell me how much soda water is coming in, and it's also feeding back that flow rate so that I get the correct ratio of soda water to color. At this side of it, I have flavoring. This is color to flavoring ratio coming into my summing junction, which is controlling another motor-driven valve, and this is my flavoring input. So I've got a flow of flavoring coming in to the system. Another flow meter, which is feeding back the flow rate of the flavoring. And I'm looking at the comparison of how much colorant versus how much flavoring, and it's a ratio, so that at this point, I've got a good ratio or a good mix of soda, water, colorant, and flavoring. So it's all done with ratios and ratio controls. There are other topics that will be covered and later in course, which are override control, selective control, a duplex or a split range control, and a auto selector or cutback control. These are all advanced topics. They are talked about in Unit 12 of your textbook. Please take a look at them. But again, you will not be responsible to answer anything complicated on any exams. But you should know what these control systems are and the basics behind them. Unit 13 of your text covers dead time. This is another advanced control concept, and it can be defined in many different ways. But for the most part, dead time is the amount of time between a change in an input and the start of a resulting response in that output. It is a definite delay that is deliberately placed between two related actions. Notice the word, it's deliberately replaced. We intentionally add dead time to the system to avoid any overlap that could permit any particular event from taking place before it should happen. So it really provides a lag or a period of time when there is no control occurring. Let me try to explain that a little bit on this blank slide. If I'm going to attempt to draw something that looks decent. So here I have a graph that I'm going to do time versus temperature, I guess. And I'll put a set point here. Anybody who's taken EMEC 245 has seen this graph before. So this is my set point. And I turn my process on, and my process starts coming up to the set point. It will usually overshoot and then recover. It'll probably undershoot, and you get this type of effect going on. This is actually very undesirable, by the way. But what I'm using is nothing more than a heater. Let me draw a heater that's being controlled by a contactor or a relay. So when I need heat, the relay coil energizes. So I may need heat here. So I'm going to say if I need heat, if heat is needed, then energize the relay. Another way I could do that, let's see, if my process variable is less than my set point. So in PLC terms, I could say I could use a less than instruction. And if my process variable is less than my set point, I can then turn on my heater. I'm sorry for this crude drawing. So what's going to happen is, and let me change the pen color here. We'll make it a dark blue, I guess. Is that at this point, at all these points in time, my heater's on. But when I get to the set point, since my process variable is no longer less than the set point, the heater turns off. So my contact just opened. Now the thermal dynamics in the system are going to allow this process to keep heating. Naturally, it'll gradually slow down, and and come back to the set point. But as soon as I drop below this set point, this contact will close again because I need heat. But heat doesn't turn on immediately. Well, the heat turns on immediately, but the process doesn't heat up immediately. So my temperature starts to drop. Before it starts to recover, I get the set point, excuse me, the heater turns off, and that'll continue to do that all the way across to the point where we get the system that years ago they used to call it a bang-bang system. And they called it bang-bang because the contactors were closing and opening and closing and opening and closing. Bang, 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 bang. Not very good for the contactors. So what you can do is put a little bit of dead time in the system. So I might put, and it's not going to be easy to show on here, I might put some dead time in the system, DT for dead time, whereby I'm not going to turn this relay on and off as often. I'm going to turn it off here and allow the thermodynamics to take it up to this point. But then I won't turn it on again until I get to here. So I change, this is dead time. So in this area, right in here, in these areas, I have no control whatsoever. Now this is not a very good example of dead time, but I hope it shows that within a dead time, you can control when you are not doing control to prevent chattering, to prevent relays from not making and breaking consistently. So that's all I want to say about units 12 and 13. Like I said, they are quite complex in nature and topic. Get as much of it as you can out of this topics, and just understand the basics. Again, if you have any questions, please post them in the questions discussion topic within Blackboard. And if you really need to, or if you want to, we can do a live session either individually or as a group through Blackboard, so we could see each other and talk to each other live. So I'll see you in the classroom. Bye.